Thank you, and thank you for being here. Now I'd like to introduce our first speaker in the Gold Science Communications webinar series, Dr. Richard Eastis, who received his PhD in physics from the Johns Hopkins University. Richard is currently a research scientist at the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics. Prior to coming to LASP, Richard led the Florida Space Institute at the University of Central Florida. He led their space environment research program. Richard is a physicist specializing in the use of remote sensing data for space weather applications and space environment research. His primary expertise is in ultraviolet remote sensing, and he's one of the world's foremost authorities on the use of far ultraviolet molecular emissions for remote sensing of the Earth's thermosphere. Richard is the principal investigator for the NASA Gold mission, which successfully launched on January 25th of 2018. Richard, I'm going to pass you the ball if you want to go ahead and share your screen with us.
Okay, see if I can make this happen.
Thanks for being here.
Yeah, there's the PowerPoint. Okay, share that. And is that...
Just go ahead and click on the either presentation mode or...
Yeah, so you can all right.
There you go.
So are you seeing the presentation mode screen?
Yep, we're seeing your PowerPoint as it should be viewed on the screen. So it looks
okay, good, because there's there's a presenter screen also that I see, so I just wasn't, sometimes these things get mixed up, and I have to discipline it a little bit and just remove the second monitor. Okay, thanks for the generous introduction, Tom. I appreciate that. As Tom said, I'm the PI for the mission. This is one of actually two missions that the Heliophysics Division of NASA is flying to look at the boundary between Earth's atmosphere and space. The other mission, ICON, Ionospheric Connections Explorer, will be launching later this year. These two complement one another very nicely because Gold's getting observations, a set of observations we've never had before from geostationary orbit, looking back at the Earth. So we're getting an overview, and ICON's flying in low Earth orbit, where we have able to make observations that give us some details that we can't observe from geostationary orbit. So anyway, this is a nice, wonderful combination, and we were another PI and I were both excited to hear that the other guy had been selected also when we heard the news several years back. So let's see if I can make this advance. There we go. As Tom mentioned, Gold was launched in about a month ago, just a few days more than a month ago, from French Guiana. As some of you, I'm sure, have heard, there was a little bit of a hiccup on the launch, that the inclination, actually they've done an investigation, Arianespace has, and determined that there was an input error, so resulted in the satellites being put into the wrong inclination, 20.6 degrees instead of 3 degrees, which was planned. So this essentially has a negligible impact on the mission, because it just delays us getting into orbit by a few weeks. We've been waiting for years to get the data, so a few more weeks is really not a big concern to us. We can still do all the science, still get wonderful observations. As I've shown here on the slide, let's see if I can do this, point to the right places. Can you see my pointer? Just as a test here, later on I'll need this.
Yes, we can.
Can you see it, Tom?
Yes.
Okay, good. Open the detector doors a few days after launch. So some of the crew actually flew directly from French Guiana over to Toulouse, where Airbus was commanding the satellite. They were able to open the doors, so we know that the instrument survived launch, at least enough to turn on, open the doors. So that's good news. We were certainly very relieved to see that. It's always launch is always a stressful time because of the risk and some risk involved. It's never risk-free. Launch isn't. So anyways, we know that the instrument was able to function. It will be off until we get onto geostationary orbit. as we need to be on geostationary orbit in order to get the high rate data, which the science data is high rate data. So that comes down through a transponder that is on the satellite, so we can dump the data down directly to the ground. We don't store any of it on orbit. As is shown here on the slide, we expected commissioning to begin in late August and operations actually to begin in October. So we're on the way. And one reason we want to do this is the view we get from geostationary orbit. This is a GOES satellite image. It's a little bit further from a position a little bit further east. Actually, the cloud images, we're used to seeing these from on the evening news or from various sources. Actually have superimposed on here some images from another NASA mission that shows the Earth's surface. Although the goal doesn't see the Earth's surface, it just sees the upper atmosphere. This gives you the concept of, or at least an idea of what the view that we will have from geostationary orbit. Of course, the cloud images have revolutionized our understanding of terrestrial weather. So this set of observations we're having is the first set of observations that we'll have of this boundary region from geostationary orbit. Be able to do this, of course, continuously from geostationary orbit. You're sitting over one location, which is wonderful for being able to track the changes in the upper atmosphere. Something that from low Earth orbit, the time scales are about a day to revisit the same location with the same solar illumination. And in that length of time, things can change dramatically. So we've always had trouble understanding whether the changes we're seeing are due to changes in time or just changes in location. Because the time we get back to the same location is it's about 24 hours later. And at least for a large scale view, unless we have with the inclination that covers most of the Earth, orbits takes about a day to get back to the same location. And by that time, the changes that we're seeing that occur on the scale of an hour frequently are difficult to understand. Let's see, I don't think that advanced. Okay, just to give you, I've mentioned some of the details about the SES-14 Satellite, is the host mission for GOLD. GOLD is mounted on the deck. Actually, you can it's very small here, but it is shown in this image of the satellite. It's on the Earth-facing deck. It's some rectangular apertures at the front of it. There's two apertures. It's identical imaging spectrographs. Each of them observes the same wavelength range, and this gives us some redundancy and some flexibility and the signal to noise we needed to do some of the planned observations. Of course, LASP built the instrument here in Boulder, Colorado. They have done this similar instruments, somewhat related instruments anyway, UV instruments for decades. These sorts of instruments can survive a long time in orbit. Some of them planetary missions and even low Earth orbit missions have survived for a decade or more and continuing to make observations. So of course, this is there's the two channels. Each of these channels makes observations of the disk. That's basically the Earth's surface, what you're seeing when you're looking back at the Earth's surface in that previous image. Sort of where if you could see the surface up there, you see the continents. Of course, we're going to only see down to about 110 kilometers, about around the boundary of Earth's atmosphere and space. And these emissions, reason is the emissions that we're looking at get absorbed in the Earth's atmosphere. So they can't be observed from the Earth's surface, and you can't see the Earth's surface or further lower altitudes just because of absorption of the atmosphere. We'll use these data to make, in the daytime, to make images. We get images of the composition, which is O to N2 density ratio. Remember down here on the Earth's surface, of course, most of the atmosphere, almost all of it is molecular oxygen and molecular nitrogen. when we get to the altitudes at this boundary region, there's a lot of oxygen, atomic oxygen also. So we'll have images of the density ratio, which is something that we've observed before from low Earth orbit. These observations in low Earth orbit have revolutionized our understanding of the Earth's, this boundary region, but we've never had the temperature information to go along with it. And GOLD will be able to supply that. From the same observations, we'll get the composition and the temperature over the surface of the Earth. At night, we'll be observing also the emissions that we're looking at in the daytime. Most of them aren't there. There are some emissions at night that tell us about the peak densities in the ionosphere, which is another, I'll talk about the thermosphere and ionosphere in a few minutes. Those are sort of the two overlap, basically coincident regions of the atmosphere where we're observing. We'll also be observing the in the limb, which is the basic, when I say the limb, that's really just the horizon of the Earth. You're looking back at the edge of the Earth, and we look at how the emissions change with altitude. We can look at the Earth's emissions. It gives us temperature at the top of the atmosphere. And we can also look at the stars that are coming through the Earth's atmosphere. And that tells us some information, gives us some information about the molecular oxygen densities. In the wavelength region we're looking, 132 to 162 nanometers, the Earth's atmosphere doesn't emit, but it does absorb very strongly. So that's, this is the reason that some of these emissions don't get to their surface, is because of this absorption. But we can use this absorption if we're looking at some UV stars to tell us what the Earth's, what the O2 densities are, how the density is changing. So these will be a series of observations on the limb of the Earth or the edge of the Earth right on the horizon. Okay, just to add a couple more things and just give you a picture of where the data is coming, where the center, basically where the satellite will be based. It's over the mouth of the Amazon, as I mentioned earlier. This is shown in the image here in the SES-14 gold subsatellite point, and the data is actually coming down through a station in Maryland, a ground station, receiving station there. So its geostationary satellite stays over this one location, and the data is transmitted to the ground in real time. We don't store any of the data on orbit. So one of the things about this is nice thing about being on a communication satellite, there's plenty of data rate available to you. They're glad to provide more. So we've taken advantage of this basic capability and just decided that rather than trying to store data or trying to compress data, we just send, actually each photon has a location of the detector. So we send those locations down to the ground. So then we don't have to, we can, on the ground, we can just change our minds about how we sum things up, how we combine things. Typically on a science mission, the data rate requires you to combine things before you get it down to the ground, and after the fact, you can't unravel it. It's already combined to that level. But with gold, we have a lot of flexibility, so we're using that. And it gives us, really makes life simpler in some ways, because we can decide after the fact that if we didn't get it quite right, we can change it if we need to. So it's a luxury for a science mission to have this kind of data rate that we've, no science, at least science missions I've been accustomed to, don't have. I guess there are some science missions for NASA there's a Solar Dynamics Observatory, which is on a geostationary satellite, which also has some very high data rates. But most of the missions that have flown that I'm familiar with, that's an unusual aspect to have this kind of data rate. I'll talk a little bit about the satellite just to give you some idea of what this SES-14 satellite is. It is a communication satellite. It's this primary mission. So we're a hosted payload on this satellite. So it's just get into geostationary orbit is there's not a lot of opportunities on science missions because it's a long way away. The satellites are big, and traditionally the Earth's thermosphere-ionosphere observations have been done from low Earth orbit, where it takes about a day to get back to the same location, and that has limited our ability to make advances in this region. The satellite's a Eurostar E3000E, which means it's electric propulsion. It has a design life of 15 years, which is sort of typical for these satellites, geostationary satellites. And this one uses electric propulsion to get onto orbit and for station keeping. There have been communication satellites that used electric propulsion for station keeping before, but there haven't been many. This is sort of unique, sort of a new aspect of this mission in that it uses electric propulsion for orbit transfer. So that's the reason it's taking us about 6 months now to get onto orbit. I guess 6 months from launch, I should say, about 5 more months. The satellite will be on geostationary orbit and begin checkout of the payload and the satellite. It's about 4.5 tons, metric tons satellite. So it's a significant size satellite. It's about 50 yards from wingtip to wingtip. Okay, now the instrument itself, I mentioned there's 2 channels. This diagram shows you how they fit together. Each of the channels is identical channels, and in the middle between these 2 channels, there is an electronics box that contains some of the electronics for the 2 channels. Putting them in the middle here provides some extra shielding. So on geostationary orbit, we need to shield more than we would in low Earth orbit. Earth's atmosphere is wonderful for us because it shields us from a lot of radiation, a lot of particles. And once the satellite goes to geostationary orbit, it doesn't get the benefit of that shielding from the Earth's magnetic field, Earth's neutral atmosphere to protect it from all the radiation like it does in low Earth orbit or at the Earth's surface. Also got some vital statistics here. It's 37 kilograms, which means it's about 80 pounds. And it's and just for the size, I think it shows you some dimensions here. This is maybe a little bit bigger than a microwave oven, slightly, or a big microwave oven, or a really small mini fridge. So it's yes, it's not a massive instrument, but it's certainly wouldn't want to drop it on your toes. As far as science missions go, it's relatively smaller than a lot of the missions that have flown. Okay, now what we'll be looking at, the purpose of the mission is to answer some science questions about the forcing of the thermosphere-ionosphere. The thermosphere-ionosphere is the neutral atmosphere, and the ionosphere is the charged atmosphere in this part of the atmosphere, or part of the altitudes that we're looking at. We've known for decades that the forcing from above was, we've looked at this and tried to understand the changes in the thermosphere-ionosphere based on just looking at the changes in the forcing. We know that there's forcing from geomagnetic storms. These are very episodic, can change dramatically in just an order of an hour, or so. There's big changes, can occur from that, as much as occurs over a solar cycle typically. And the other source is just the sun's ultraviolet radiation, extreme ultraviolet and X-rays, and these 2 have been sources that we've looked at for a long time, and we know that they do a lot of forcing and cause a lot of changes in the upper atmosphere. Just in the last decade, approximately, maybe it's slightly more than a decade ago, we began to understand that the forcing from below is also a significant factor, and that the Earth's lower atmosphere, or at least there's waves and atmospheric tides are propagating up from below that also influence this region of the atmosphere. And only to, now we're beginning to understand this, that these are significant influences. We have some really good models of the forcing, how the forcing can contribute, and the models just now begin to catch up with actually including the forcing from below into this region, because most of the models we're getting to altitudes where it's really at the boundary of them, so they carry up to about 110 kilometers, and they're now being extended, but they only recently has this happened, as people began to understand that this is a significant source of influence. And we are also looking at some of the nighttime ionosphere. There's some effects in the ionosphere that, because of the forcing from above and from below, we know that both of these influence the nighttime ionosphere, and the nighttime ionosphere is where there can be some disturbances that cause problems for some of the systems we use, such as global positioning systems, communication systems, and these have some significant impacts on those systems. The evolution of the ionosphere does.
Richard, I have one question for you.
Yeah.
It comes from Christopher Mick. And
Okay.
he asks, will CMEs or coronal mass ejections have any negative impact on data gathering for the GOLD mission?
They will probably add, we expect them to possibly add to the noise, but we don't expect to have the interruptions from this. So, of course, the CMEs will be influencing what's happening, what's happening in the atmosphere below us that we're looking at. But we are, we've done the modeling for how the shielding of the instrument, and we know it will increase the noise some that we have, but that's not, there are other sources of noise, so we think we'll still have good observations.
Great. One other question that just came up as well, somewhat related to what you just spoke to, is what density does GOLD measure during the nighttime ionosphere observations, neutral density or electron density?
Okay, good question. It's measuring electron density. Actually, the peak electron density is what it measures. So the nighttime emission rates are very sensitive. Actually goes as the density, emission goes as the electron density or ion density squared, they're equivalent. At least we normally think of them that way. So it goes as density squared, so it's very heavily peaked on the density. So if you fall off a factor 2 in density, you've fallen off a factor 4 in the emission that's contributed from the region. So it is the peak electron density is what we'll be measuring at night.
Great, thanks.
Okay. Okay, so I mentioned the thermosphere and ionosphere already. I just, on the left here, the red line shows you the temperature of the thermosphere. It's the neutral atmosphere. And as you can see, as shown in the figure, it increases with altitude. And we know that the sun's output, or sun's input, can change this over the solar cycle, I'll just show you in a moment. But also, it can change dramatically due to geomagnetic storms. It can change in the region that we're looking. Typical temperatures are, say, 600 degrees, and the temperatures can change by hundreds of degrees, actually, in just an order of an hour or two, due to geomagnetic storms. Of course, the atmosphere is absorbing energy, is dissipating the energy from the from the sun to ultraviolet radiation. And when it does that, absorbs that energy, the energy goes into the constituents there. It disassociates the molecules and atoms and causes production of the ionosphere, which is the other overlapping region, which is shown here in green, the electron density of the ionosphere. So these two coincide with one another. Thermosphere is much denser than the ionosphere, and it actually influences the density of the ionosphere significantly, depending on what the atomic to molecular density ratios are in the thermosphere. Shown on the right here is just the some of the densities, how they vary with altitude. As shown there, the atomic oxygen becomes a dominant species at higher altitude. In the region where we're looking, there's significant molecular nitrogen and atomic oxygen. And these changes in this are one of the things that this composition O to N2 density ratio is something we were looking at. And the temperature of the thermosphere is another quantity we'll be imaging, getting images of those. So as I mentioned earlier, these things can change dramatically over this in just hours. Talk a little bit here about just how it varies over a solar cycle. This sort of shows you the solar and geomagnetic forcing, how the amount of energy going in. And as you can see from this plot, the black line is the solar power, the solar EUV, and the blue lines are the geomagnetic storms. And most of the time, this solar EUV dominates, but during the storms, the geomagnetic energy dominates the process. So, and these vary about 11-year solar cycle. The sun's output varies about approximately 11-year cycle, and you can see this in both this, well, of course, the solar EUV and in the geomagnetic storms. You can see in both of those. And so what we'll be looking at is the, of course, shown here the E region, which is really, we will be, normally don't see except in the aurora, because the auroral region, the emissions when there's storms, the auroral region, which is sort of shown as up here near the North Pole, you can see a colored region where there's auroral emission, and during storms, that region will come down. It's an auroral oval, they call it sometimes, and that region of emission will come to lower latitudes, and we'll have a much better view of it. Actually, one of the ironic things is that the NASA has flown several missions in high inclination orbits, so they go out, they come in low into the atmosphere at the lowest point, and they go out high, and have the apogee, the highest point over the North Pole. But when there's geomagnetic storms, it tends to they don't have as good a view of the aurora often, because it goes far enough south that it's getting out of the field of view more. So we will actually have from geostationary orbit, being sitting on the equator. If there's a really dramatic storm, it's been known to, aurora has been known to be seen over Houston. If it gets over Houston, we'll have a really great view of a geomagnetic storm if it gets that low. Other panel here shows the neutral temperature, as I mentioned earlier, the O to N2 ratio, and the F region electron density. Now, I have a movie. Stan Solomon did a simulation of these just so we could sort of see what these would look like in a storm. And if I play this, at first it'll play just this is for sort of a moderate storm. It shows the E region, so you can see when the storm commences, the aurora came to lower latitude. I sort of got behind there. So anyway, here's now showing the neutral temperatures, how those change during the storm. Now next, the O to N2 ratio will plays through for a series of hours, showing you how the O to N2 ratio changes. And last but not least, it shows the electron densities in the F region. So this is what we'll be looking at night, is the F region, well, and the aurora. We'll see that also at night. So, of course, these are all happening at once. So really, the primary things we'll be observing is the neutral temperatures and O2 into in the daytime. We will see the aurora in the daytime also, but at night. And the electron density, peak electron density. This just shows you that electron density about 300, which is near the peak. So we'll be observing those. Depends on the time of day is what we really have the best view of. So if I go to the next slide, I'm going to play these all at once. Yeah, so you can see that all this is going on at one time. So that, just in the order of an hour or so, there's big, really drastic changes in what's happening in the Earth's upper atmosphere. So this region of the atmosphere, of course, the nighttime atmosphere changes, the F region changes, and the E region also. The atmospheric distance change that can dramatically affect the systems that we use. Neutrals affect things too. For example, satellite drag can cause loss of satellites just because there's more drag on it, its orbit changes, and it doesn't go where you expect it's going to work with. Really high orbits aren't affected, but there's a lot of satellites in the low Earth orbit that are affected by these changes. Okay. So this, gives you a picture of how things change with a geomagnetic storm. And this is just a moderate storm. The temperatures change by hundreds of degrees and tens of percent or more in density. So it's significant changes. Now, the other piece of what we're looking at is trying to understand is forcing from below. And this is just a simulation of some of the model of the tides that one of the guys who works with us did. And as I mentioned earlier, that a lot of the models don't go up completely in this altitude region we're looking at. This is 160 kilometers approximately we're looking at the daytime. It's a region that's difficult to reach with in situ measurements. It's too high to get to balloons. It's too low to get to the satellites typically, except for briefly. So there's very few direct observations, and being able to remotely sense the temperatures is something we haven't really developed. We have the instrumentation.
Richard, excuse me for interrupting. Your audio seems a little unclear. I'm not sure where your microphone is located. It seemed to coincide with when you started the video, so it might have been a bandwidth issue, but it seemed to now continue onto this slide as well. So maybe we can just do a quick check and make sure your audio is clear.
Okay.
It sounds better already. I'm not sure if you did anything, but that sounds good.
Well, I think part of it was that the fan on my computer started blowing.
That could be it too.
My computer got warm, so that was causing some interference on the microphone. So sorry about that.
That's okay. Yeah, so it might be when you start a video if that fan might kick in again, but just something to be aware of. Thank you.
Okay. Well, this just shows some of the tides. Just shows you a simulation of these are atmospheric tides driven by actually the sun, and at least initially, and then those modes, different tidal modes generated within the atmosphere. So we know these sorts of things are influencing the ionosphere, thermosphere, and ionosphere. So these have a significant influence. And the other thing that has an influence is some of the this is relatively recent, like in the last year or two, one of the guys at HOA NCAR, High Altitude Observatory, NCAR's High Altitude Observatory, did some modeling. And the models have been advancing. They finally got to the resolution that they could do a little bit better simulation of what's happening. It doesn't go yet up to the altitudes that we're looking at, but he did do some modeling, takes it to about 110. And this is for a typhoon over the Pacific. And looking at the temperatures around 110. Now the temperatures as you go up, if these are gravity waves is what these are called. So you can see the concentric rings from the typhoon, since it's over the Pacific. And as you can see, they cover most of the, basically a hemisphere or more of the Earth. This is just incredible. Of course, we'll be sitting over Atlantic more, but the similar things would happen with hurricanes over the Atlantic. So we will certainly be looking for this sort of influences when the satellite's flying. So I recently moved from Florida, and I always said that I have something to look forward to when a hurricane started approaching Florida, other than just boarding up my house and getting out of the way. So, of course, these are hundreds, about 75 degrees at 110. So as you get to higher altitudes, there's actually, this is a big change at 110 kilometers. This is really, as you can see, the temperatures go from about 155 to 225. So 75 is about a 50% change in the temperature, increase in the temperature. So as you go up, it's even increases even greater because the atmospheric density is decreasing, and for the wave to reach there. This is part of the debate that we've been having with the science community has been having, is which of these tides get up there and waves get up there, and which ones, where do they deposit their energy? So we'll be looking at this. And these have some significant influences on our understanding of the thermosphere and ionosphere that, this is just shown here. This is a slide I borrowed from a colleague at NOAA space here in Boulder, and it shows some simulations or some modeling that was done with lower atmosphere that's independent of, some atmosphere independent of the lower atmosphere and coupled to the lower atmosphere. So these changes, like you're seeing in some of these previous slides from tides and gravity waves, you propagate them up. On the right-hand side, it shows you how much structure this can generate. So these sorts of things actually have significant influences on some of the systems that people use and rely on every day. Okay, talk a little bit about how the observations, how it makes observations. Each channel has an entrance slit. It's a spectrograph, imaging spectrograph. So it's a spectrograph first. So then we just sweep as shown here, we sweep the slit across the Earth. The slit's long enough to cover about half the latitudes. So we sweep the slit across, one half of the Earth, and sweep it across the other half. Combine all those slit images, and that gives us an image of the Earth. As I mentioned earlier, of course, here shows you some of the observations we're doing. The different modes of, day, night, what we're looking at. So I've talked about that some already, but I think this gives you a little bit of a picture of how we're doing the observations. And the instrument's designed such that it does can scan the full disk in a bit less than 30 minutes. Each channel can. And it also allows some time, about 7-8 minutes, for doing a limb scan or a stellar occultation. So we'll combine those throughout the day. This is, again, Stan Solomon at High Altitude Observatory from INCAR. Just did a simulation of what one of the images, or image at one wavelength, would look like, just from the models that are uncoupled to the lower atmosphere. So this is a third atomic oxygen emission. Of course, you see the emission that's really, we've shown the outlines of the continents here underneath this, just to give you a reference point. But as I mentioned earlier, we do not see the surface of the Earth. We only see down to about 100, and a little bit above 100 kilometers at best. But you can see this is sitting on the edge, or sort of sitting near the sunset. And as you go from the left side of the image to the right side of the image, you go from day to night. And on the night side, you can see there's some structure in the lower latitudes and the nighttime ionosphere. And you can see this structure, that there's bright bands on each side of the magnetic equator. So we'll be looking at night, we'll be looking at that low latitude ionosphere, at those brighter regions, seeing structure in those. In the day side, we'll be looking at the O to N2 ratios, the neutral temperatures, and of course the limb. We can look at stellar occultations day and night, and we'll be looking at the limb in the daytime.
Richard, there's one question about this image, and that is, why are the edges along this left limb are a lot redder? What is the significance there of that color bar on the right-hand side?
Well, what happens is, as we look out towards the edge of the Earth, have a longer path through the Earth's atmosphere. So we see emission from a greater, there's more emission to sum up along the line of sight. If we're looking down vertically through it versus an angle through the atmosphere, there's less emission just in a vertical view than there is at this looking at it sort of more edge on. And so this image shows some of the brightening that occurs near the edge of the Earth. It's sort of fortunate for us because, that in a way, because the result is that the brightness across the Earth is pretty much uniform, even though the sun angles may be varying on us. So it smooths things out a bit for us. Okay, just talk a little bit about some of the benefits of this mission. Of course, NASA's is working hard to understand how the system, the Earth system is coupled. So we have a lot of measurements of the sun's inputs. The GOLD mission and the ICON mission will be looking at how the Earth's atmosphere, this boundary between Earth and space, Earth's atmosphere and space responds. So this is where a lot of the effects are for GPS, for communications. To help us develop some advanced models. Already, we've seen that people are pushing the models to higher altitudes, trying to understand this region of the atmosphere, the region where they didn't have any measurements before. It's the trouble that the modelers always have is without any data to guide them, they can come up with lots of different answers. So now there's going to be some data to help guide them and help test the models against. They're pushing the models to higher altitudes into this region of the atmosphere from below and trying to make sure that they understand it. I mentioned, I think, some of the benefits also for communication systems, navigation systems, and I think this is a mission where we will have day to day. We'll be able to sit. There'll be a series of images, but you can watch them. We'll be able to look at them like basically it's a movie we get of how the Earth's atmosphere is changing throughout the day, versus previous missions where we took us a day's worth of images to get a picture of how the Earth's changing. We'll be able to sitting in geostationary orbit, we'll be able to watch the change over at about a half-hour cadence and see how things are going. So I'm looking forward to this.
Richard, why is the satellite so heavy at 4.5 metric tons? Do you know what contributes to that mass?
Most of it, well, actually it's a very light satellite for the amount of payload it has, communications payload, because of electric propulsion. But there's a lot of there's a lot of electronics on it for communications. That's where a lot of the mass is. Also, just the solar panels, the structure to support that. So it's this thing generates a lot of energy, kilowatts of energy. So it's that's basically what where the mass goes. Most of it, the mass is in the communications payload, which is the primary mission of the satellite.
And the same participant had another question. Are we using a telecom satellite to relay the data?
Oh yes, we are sending the data to on board through the satellite to one of the transponders, and they're downlinking it from one of the transponders on the satellite. So it's no data stored on the satellite. It all's linked down to the ground. locations of every photon that's detected is being sent to the ground.
One more question while you're on a roll here.
Okay.
How can we best prepare for working with gold data? Will there be test data sets and/or data manuals available before the first public data release?
There are some users manuals. So what we should do is put some links, I guess, to on the Gold website to some of these, because there is some documentation already available about the instrument. It's evolving some, but there is some information available about the observations.
Is any of that available in the publications that have already been issued?
There is, I don't think the listing of the user's manual and stuff like that. There is one publication out that talks about the mission and what the observations will be, and so that's the is one place to look. But there, as we get closer to being in operation, the manuals will become available. We will be posting that information on the website for people, because we users need to make it. Users will need information to help them understand what the data is, and that, of course, this is part of the reason we're doing some of these presentations, where we're recording these and having these available to help people understand it.
There's a data products section to the Gold website, so we could put the manuals there to have folks access them. Yeah,
all right, good point. I knew that there was some stuff up there, some details, but there's certainly more information than we have there at the moment. That's it's not. We may need probably. I think we're putting some finishing touches on some of those, so not sure that they're publicly available yet, but they will become publicly available.
Great. Another question: in case of something happening, I'm not sure what this person has in mind, but can gold hold data by itself?
No, there's no storage capability on board. We do have some data that's going to, just housekeeping data that's going to the satellite itself. So there's actually I mentioned that there are the high rate data, which is the science data. The housekeeping data comes down in that data set, of course, but there's also a second set of data, smaller data, that's just housekeeping about, such as temperatures of the instrument, voltage levels, things like that are made relate to the spacecraft also, and the spacecraft operators can monitor this to help us help track and to make sure that the instrument is safe, that there's no issues there. So they will have, SES has operators who are 24 hours a day who are monitoring the satellites. So they will be monitoring it with that housekeeping data we send them, and the Science Operations Center here at LASP will be using that data when they get it, but also the high rate data, the housekeeping information in that, to monitor the health of the satellite, or health of the instrument, actually, I'm sorry, not satellite, but the instrument. So, but the science data is all coming down through the high rate, which is only available as through the downlink. There's no storage on board. It simplified the instrument a lot.
Richard, why atomic oxygen and molecular nitrogen versus molecular oxygen to molecular nitrogen? What are we learning from those ratios?
Okay. The reason we don't do molecular oxygen is it doesn't have, we don't have a capability to do that, or at least not in the ratio directly. It absorbs rather than emits, and it's that wavelength reason that we're looking. So that's one of the reasons we're looking at the stars on the stellar occultations on the limb, stars rising or setting, either one will work. we look at those to tell us what the density is, O2 density, and how it's changing in the atmosphere. It's partly this, that we're using some techniques that have been proven on previous missions to look at atomic oxygen versus molecular nitrogen. Both of these emit, at least emissions that are in this wavelength region we're looking at. They're relatively bright. They're not bright in comparison to the sunlight that we see with our eyes, but for UV emissions, they are strong enough that we have good signal to noise to work with them. There's not a lot of atomic nitrogen emissions that are well understood. There are atomic nitrogen emissions in the spectrum, but there's the mechanisms for their production is complicated enough that we are not confident we can understand them accurately enough for scientific analysis. And the techniques haven't been developed to use those emissions, but they have been developed to use the atomic oxygen versus molecular nitrogen emissions, and those that get the sort of wandering off here a little bit, but the O2 and N2 are similar in density. We typically expect them to behave similarly as far as the changes in density, percentage-wise anyway. And that ratio is important for the ionosphere. In the ionosphere, the recombination is much faster if there's more molecules. So the ionospheric density will be decreased due to that if there's more molecular versus atomic. So that's the reason we're looking at those. So it's an important marker. And the other piece of the puzzle here is that we're looking at the temperatures and the composition. These, for example, for many of the tides, at least the stronger atmospheric tides, these two are out of phase slightly. So enough, they're out of phase so that the combination of the two gives us, each of them is giving us a separate piece of information. And the combination of the two helps us understand what's happening that we wouldn't be able to understand with just looking at one of them. So is there any further question on that? Or I probably got a lot more than people were looking for, but anyway.
There is one additional question, not necessarily related, but will gold data impact climate change models?
I don't know that it will. Who knows how data will eventually be used, but that's not the climate change models are not the goal of this mission. I guess not. Well, not. When I think of climate change models, I think of the lower atmosphere. I guess in the sense that that climate, it's far enough disconnected that I don't know that it will have any influence. Certainly, part of what we're looking at with gold is, previous missions have been looking at the climate of the thermosphere-ionosphere, sort of the long-term, how the seasonal dependence, solar cycle dependence of the thermosphere-ionosphere system, and haven't been able to look at the day-to-day changes really readily, at least not the shorter-term changes that we know that occur. So, in a sense, that this mission will be looking at the weather of the thermosphere-ionosphere, where before we were looking at the climate of the thermosphere-ionosphere. But if you think about the climate of the lower atmosphere, no, I don't know that there's any. We haven't been don't have a clear connection to that.
Great, thank you.
Okay, so let me just wrap it up here. I think some of this I talked about before. I think the one thing I'll mention here is that by the way we're looking at this, by being able to sit above the same location on Earth, look at a half-hour cadence, for the first time, we're really going to have a good capability to separate changes in time from changes in location. This mission, of course, is looking at sort of a global scale changes, how the changes are developing over the whole hemisphere of the Earth. And this provides a lot of context for some of the low Earth orbit missions and for ground-based observations. So it'll help us put those into context, something we've had trouble doing before. The operations are planned for 2 years. They'll begin in about October. Of course, this is the way NASA sets up the missions. That's a 2-year mission. It's a nominal mission. If things are healthy and we're getting good data, then at the end of that, we certainly would be proposing for extend the mission to continue the observations. And by being on a geostationary satellite with a 15-year life, nominally, we have a good chance of extending that. And we actually have agreement with SES for extension of the mission for us. I think we have it set up for 3 additional years as an option for 3 additional years. So hopefully it will continue well into the future. So thanks. Appreciate your time.
Thank you, Richard. Thanks for being here with us today and kicking off our series of webinars. As I mentioned, we'll be back March 21st, and we'll have more of an engineering focus talk that'll go into great detail about how the instrument was designed here at LASP. Let's see if we have any other questions. So here's one from Joseph. Although this instrument is centered for the discussed research goals, is there any possibility or useful observation for the GOLD mission in assisting the National Space Weather Prediction Center for better space weather forecasting and real-time observations for that program?
Yes, the data is being sent directly to the ground. It's available in basically real time. So yes, there is a capability or possibility of doing that. People, I'm sure, will want to see that we're providing something that's of value to them. But I know from my experience that other contacts also, that one of the concerns for ionospheric modeling, which is one of the things that is used by civilian and other agencies, is that the composition information, that you need better composition information in order to do a better prediction of the ionosphere. And so the data itself will be valuable for helping guide the models as input to models, and also just the observations will help us develop better models. So that's one of the outcomes, will be one of the outcomes of this. We're already seeing this, that the models are beginning to be extended to higher altitudes. So we have capabilities to modeling some of the tides that are coming up from below. And seeing that, we need data to help us understand the tides from below. Typically in the past, we've always had for thermosphere and ionosphere, there's been this day-to-day 10% type of error that we were only able to overcome by inputting observations. And the observations, of course, the area over which they would help you was limited. So by having a whole hemisphere, being able to observe essentially a hemisphere, we can provide data over a large area, and those inputs for composition, for ionospheric densities, will be valuable for helping improve the forecasting and prediction. But that's not the purpose of the mission. We're really focused on the science, which will, will feed into the prediction, and the data could be eventually used directly in some of these capabilities.
Great. Well, I think we're about up to our time limit. Richard, again, thank you for being here and for your wonderful summary of the mission. I think we're out of questions, so we'll go ahead and wrap up. As I mentioned at the beginning, this presentation will be available to watch online I posted the link at the very top of the chat. I'll just repost that again so everyone has that available to them. And we'll also have audio and transcripts available there, as well as a PDF of Richard's presentation if you're interested in accessing that. Thanks everyone for joining us, and we hope to see you back this same Zoom room in March. Take care, everyone.